Okay. Okay. So we've been talking about the second fundamental form and the tension field of a smooth map F between Riemannian manifolds M and N. So so we said that F is okay. So let me just recall the definitions. So the second fundamental form, nabla df. This was a bilinear map from TPM cross TPM to TFPN, right? This was acting on a pair of tangent vectors VW at P. This was defined to be, so you think of DF as a section of T star M tensor, the pullback bundle F star of Tn. So then the tangent vector V, you can differentiate this section of that tensor product bundle with respect to V. So you look at nabla V df. This then becomes a linear map from TPM to TFPN. So this acts on W, right? To give you an element of TFPN. Yeah. VW are in TPM. And we saw that this was symmetric. So this is a symmetric bilinear map. And so it is determined by its values on the diagonal. And on the diagonal, acting on a vector V, on a pair V comma V, this could be written as a second derivative F composed gamma double prime at 0. So this is a vector in TFPN, where gamma is a geodesic in M, which has initial conditions gamma 0 equal to P, gamma prime 0 equal to V. Okay. And then the tension field, tau F, this was a section of the pullback bundle, F star Tn. This was defined to be the trace of the bilinear map, the symmetric bilinear map nabla df. And for a vector valued symmetric bilinear map from an inner product space to a vector space, this was equal to the sum over I nabla df of EI comma EI for any orthonormal basis EI of TPM. And so by the above formula, we can write this as a sum of second derivatives in these orthonormal directions along geodesics gamma I. So gamma I is a geodesics in M such that gamma I0 is P and gamma I prime 0 is EI. Okay. So we said that we looked at the energy of a smooth map. This was half the integral over M of norm df squared with respect to volume, right? Where norm df squared, this was the trace of the endomorphism df star df. So this is also equal to the sum over I norm of df EI squared, where EI is any orthonormal basis of the tangent space, right? Okay. And we saw that for any variation, Ft of F, so that F0 is equal to F, we found a formula for the first variation of energy ddt at t equal to 0 of energy of Ft was minus the integral over M of the inner product between the variational vector field and the tension field. This integral with respect to volume. Okay, so this variational vector field V was del del T at T equal to 0 of Ft. So this was also a section of the pullback bundle F star Tn. Okay. So this led us to the definition of harmonic maps. So F is harmonic if and only if the variation of energy vanishes for all variations Ft, and that happens if and only if this tension field is identically 0. Okay. So harmonic maps are exactly critical points of the energy functional. So here I'm assuming that M is compact without boundary. In order to get this first variation formula, because to get this formula, you have to do an integration by parts, and there's a boundary term. So that boundary term vanishes if either the boundary of M is empty, or if the boundary is non-empty, then you have to consider proper variations. That means variations which are constant on the boundary, constant with respect to time, T. Okay. So we are going to assume M is compact without boundary. So then we have this formula. Although the definition of harmonic makes sense for any manifold, okay, any Riemannian manifold. If it's non-compact or has boundary, then the tension field will be 0 if and only if the first variation of energy is 0 for all smooth, compactly supported variations. Okay, so you take variations which are constant outside a compact set, which is disjoint from the boundary. Okay, is that clear?
Sir, so harmonic being implying tension field equal to 0, it holds true only for compact manifolds without boundary.
No, 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 no. A harmonic, the definition, this is the definition. This is the definition. This is not a, this is the definition. F is harmonic if its tension field is 0. Okay, and this is equivalent to the first variation of energy equal to 0 for all variations which are compactly supported. So so what that means is there exists a compact K is disjoint from the boundary. Okay. And Ft is equal to F on M minus K. Okay. Is this clear?
It is, yes, sir, it is clear.
Okay, that's it. So, yeah, but the definition is just that the tension field is 0. This makes sense for any manifold, whether compact, non-compact, with boundary, without boundary, doesn't matter. Okay. Yes.
Yes, sir.
Okay, for the variation to be fine, for the energy to be finite, you would need compactness in general, right? For the energy to be finite, you would need compactness. This integral may not converge. Integral norm df squared, in general, it may not converge, right? So, so for that, you need M to be compact. That's all. So, yeah. So here, yeah, this is this characterization in terms of first variation of energy for non-compact manifolds. This is if the energy of F is finite. If F is infinite energy, then you can't really say anything in terms of variations of energy, right? It doesn't make sense. Okay. Is this clear?
Yes, sir.
Okay. Fine. So now we're going to, yeah, so as examples, so let's take a curve in a Riemannian manifold M. Okay. So then what is the tension field of gamma? The domain is one-dimensional, so orthonormal, I'm taking the trace of the second fundamental form. So I have to sum over I. You know, gamma composed with a geodesic, its second derivative, right? Sum over I. So that's just going to be gamma double prime T, right? The tangent space is one-dimensional. So this is just going to be gamma double prime T. Is that clear? The geodesic in the domain is just the identity map from R to R, right? Is this clear? Yeah?
Yes, yes, sir.
Okay, so gamma is harmonic if and only if this gamma double prime is 0, that means gamma is a geodesic. Okay.
Hmm.
And secondly, if I have a function from M to R, then what is the tension field? So this is the sum over I, F composed gamma I, double prime, 0, right? But we know that for a function, if I look at its second derivative along geodesics, then F composed gamma I double prime is nothing but the Hessian, right? So this is just nabla squared F EI, right? So this is the trace of the Hessian, which is nothing but the Laplacian of F. Okay. So F is a harmonic map if and only if it is a harmonic function. Okay. Is this clear?
Yes, sir.
Okay. Okay. So harmonic maps occur as generalizations of both harmonic of geodesics and harmonic functions, right? Both are special cases of harmonic maps. Is that clear?
Yes, sir.
Okay. All right. Okay, so then what we're going to look at today is something called the Bochner-Weizenbach formula, which is a formula for the Laplacian of the energy density of a harmonic map. Okay. Well, actually of any smooth map. It doesn't have to be harmonic, but it takes a special form when the map is harmonic. So recall the energy density E of F. This is half the norm of df squared. Okay, so this is the quantity you integrate to get the energy of F. Okay. And so the Bochner-Weizenbach formula will give you a formula for, this is a smooth function. This will give you a formula for the Laplacian of EF. Okay. So we're going to compute the Laplacian of this energy density. All right. So to do this, there are going to be a few steps. So the first thing is we have to look at the curvature of a pullback bundle. F star E. Okay, so say you have F from M to N, and E is a vector bundle over N with a connection nabla. So you can pull this back, right, to get the pullback bundle F star E with the pullback connection, say nabla bar, right? Yeah, we've talked about the pullback connection. We used it to define the second fundamental form, right? Yes?
Yes, sir.
Yes, sir.
Yes, yes.
Okay. Okay. So fine. So we want to compute the curvature of this pullback bundle. Okay. So how do we do that? So we take a section S of the pullback bundle. We take a point P and M. We take vector fields X, Y. Such that bracket XY is 0 in a neighborhood of P. Okay. And we take SI is a local basis of E in a neighborhood of F of P. Okay. So then my section S of the pullback bundle, I can write as a sum over I, AI into SI composed with F, right? Yes. Is this clear?
Yes, sir.
Okay, where the AIs are smooth functions on M, okay? So near P. So to compute curvature, I have to compute two covariant derivatives, nabla y, nabla x of S minus nabla x, nabla y of S, right? So let's compute. Okay, so let me first suppose that df of x, this is a sum over j. So this is a section of the pullback bundle, right? df of, this is a section of the pullback of the tangent bundle of n. Okay, so this I can write locally as sum over j, bj. Del del yj composed with f, right? So this is where this is a section of f star t n. Okay. And I have dfy. This is a sum over k, ck del del yk composed with f. This is a section of f star tn. So remember the pullback connection nabla bar. This is determined by the property that nabla bar x, what should I call it? ST of a section. Let me call it, I'm already using S here, so I should use some other, say T, okay? So nabla bar x of t composed f, this is equal to nabla dfx of t if T is a section of E, right? So T composed F is a section of F star E. So if you act by the connection, the pullback connection on a section of the pullback bundle, which comes from composition of a section of E with F, right? Then what you do is you look at the image tangent vector df of x. So this is a tangent vector in N, and T is a section defined on N of the bundle E over N. So this tangent vector dfx can act on this section T, right? Is this clear?
Yes,
Okay.
sir.
Yeah, okay. So the pullback connection is determined by this property. So that's why we write S as a linear combination of functions on M times sections on N composed with F, because then we can use this compatibility property, right? So what will be nabla bar y of nabla bar x of S? This will be nabla bar y. So nabla bar x of S will be what? By the Leibniz rule, this will be sum over I x ai into Si composed with F plus ai into, now nabla bar x of Si composed with F, by this compatibility rule, this will be nabla dfx applied to Si. Okay? Yes?
Yes, sir. So
Now-
now we will break everything up using the Christopher symbol and like that, right?
Well, not exactly. We can now apply nabla bar y to this, right?
Hello,
Yeah.
sir.
Yes.
Sir, I have a question. This df of x is a vector field on N.
No. It is a section of F star Tn.
Right.
But what this means is pointwise, right? At any point,
Okay. Oh, right.
this
Yeah.
at a point P,
Hmm.
this dfx, df of xp,
Hmm.
right? This is a
Hmm.
vector in N.
Right.
So over the connection in the first variable, the connection, you can put in a tangent vector in the, it only depends on the value of the tangent vector at P, right?
At P. Right. At
first
at here it's f of p. Right. Yeah.
Yeah, so this is a tangent vector at f of P. So this acts on this section
Hmm.
in a neighborhood
Right.
of f of P, right? So that is what this
Right.
is.
That's it.
Okay.
Okay.
Yeah.
Yes, sir.
Okay.
Fine.
Okay. So now let's let nabla bar y act on this. So again, you'll get sum over I so y will act on this function. So you'll get yx ai Si composed with F. Just 1 second, someone. Yeah, sorry. Okay, so you'll get Yx AI into Si composed with F plus xai, and then nabla bar y acting on Si composed with F. That will be again nabla dfy acting on Si, right? So this part is nabla bar y acting on this first term, okay? And then you have it acting on the second term, right? So here I should this again, this is this nabla dfx of Si. This is a section of F star E. So what I want to do is write it as a linear combination of sections of E composed with F, right? So for that, I need to yeah, you're right. We will need to break it up with the Christoffel symbol. So this okay, so then I have nabla bar y acting on sum over I. So dfx I was writing as sum over j bj del del yj composed with F, right? So this will become a sum over j also, ai bj, right? Nabla del del yj si, right? Now this is a section on of E on N. So I take this composed with F. Okay. Is this clear?
Yes, sir.
Yes.
Yes, sir.
Okay. Yeah. Okay. So yeah, that's it. So okay. So what do I get? Okay. So yeah, and similarly this nabla dfy, this also I can break up. So I'll get a sum over I and k there. Yeah, so okay, so this is a bit long. Okay, let me do this. So nabla I of yx ai si composed with F plus xai nabla dfy si. So then I had nabla bar y acting on this. So one term will be y acting on ai, right? So that, let me put that here. So there'll be a y ai, and then I'll have nabla dfx si. Okay, so I'll have these three terms. Okay, and then I'll have where was I? 1 second. Yeah, there was, and then I'll have nabla bar y acting on this. Okay, yeah. So okay, let me stop this session and start a new one. Okay. Okay, so we have this. So let's look. We had this term YAI from this nabla bar Y acting on this AI nabla DFXSI. And then I'll have another term AI times nabla bar Y acting on this. So that will give me a sum over I and then a sum over J. AI so nabla bar Y acting on this. So what will that give me? That will give me a YBJ. Nabla del YJ SI composed with F plus an AI BJ and then I'll have nabla DFY of nabla del YJ SI, this thing composed with F. So this DFY, again, I can expand. This was summation CK del YK composed with F. So this will, so when I expand this out, let me just do this so that then I'll get a sum over IJK, AIBJ, and then I'll get here
Sir, in the last term, yeah.
I'll get
So,
one second.
yeah.
One second. Yeah, so then we'll get nabla del YK, nabla del YJ, SI, this thing composed with F. Okay. So there's a plus here.
Yeah, this is fine, right?
Okay. Fine. So now what happens when I interchange X and Y? If you look at the first term, right, then this YX will become XY. So when I take the difference, I'll get YX minus XY. That is bracket of XY, that is 0, right? So the difference of the first terms will vanish. Then I'll have these, the sum of these two terms. This is symmetric in XY, right? If I interchange X and Y, this first term becomes this second term and this term becomes this term, right? Yes?
So can you please repeat, sir?
Yeah, if I interchange X and Y here, this XAI nabla DFY SI becomes YAI nabla DFX SI, right? If I interchange X and Y,
Okay, yeah.
term becomes this third term, right? This second term becomes the third term, right? So the sum of this second and third term, the sum will be symmetric in XY, right?
Yeah, right.
So when I interchange X and Y and subtract, this will vanish also, right? Okay. Yes?
Yes, sir, yes, sir.
Okay, so R bar of XY of S, what is this? This is nabla bar Y nabla bar X S minus nabla bar X nabla bar Y S, right? So this first part will vanish. What will remain is the second part, right? Okay, so what happens to the second part? This will be, so let's look at this last term here. There I'll get a sum over IJK. And what will happen is just the orders of these del YK, del YJ will interchange, right? So I'll have AI, BJ, CK, and then I'll have nabla del del yk nabla del del yj si minus nabla del del yj nabla del del yk si, right? The whole thing composed with f. Okay, that will come from here. Yes.
Yes, yes.
And then what do I have from here? So this is the only part I need to be a bit careful about. So I'll have a sum over ij ai ybj nabla del del yj si composed with f minus sum over ik ai x ck nabla del del yk, right? Si composed with f. Is this okay?
Yes, sir.
Yeah, so everything's okay. These last two terms are bothering me. So yeah, let me see. So this part here, this nabla del del yj, del del yk nabla del del yj of si minus this will be a curvature of si, right? So the first term here will be sum over I jk ai bj ck, and then I'll have what? I'll have r del del yj del del yk acting on si, this whole thing composed with f, right? Yes. Okay. So now I can put the sum of over j inside. This bj I can put inside with this del del yj, and the ck I can put with the del del yk because r is bilinear, right? And then when I sum over j, the sum over j bj del del yj, this composed with f, that will be r of dfx. And then similarly, I'll get r of dfy, right? Is that clear? So I'll get r of, and then I have the sum over I si. So this first term, this will be r of dfx dfy acting on s, right? Does this make sense? Yeah. What's bothering me is these last two terms, they should not be there actually. Or they should cancel. That's the last two terms are bothering me. So 1 second, let me just think. Is this okay? Yeah, this by linearity, you'll get this.
Yes,
By multilinearity, right?
right.
This is you'll get by multilinearity.
Hmm.
Let me just see these. Where did these last two terms come from? So Yeah, this is bothering me. 1 second. So here, if I did this, I get YAI. Nabla YAI. Hmm. Yeah, this term I need to look at carefully. So what do I have? I have dfx Yeah. This I was writing as sum over j bj del del yj composed with f, right? So yeah, so okay, fine. So the point is, okay, let me write, so say phi is equal to x1 to xn is my coordinates in the domain, and psi is equal to say y1 to ym. This is my coordinates in the range, right? So yeah, these terms should cancel. That's these last two terms here, they should cancel actually. They should cancel. Yeah, so actually, what is this? This last term here, this is sum over I, AI into, and then I have nabla sub sum over j y bj del del yj composed with f, right? Minus x ck. So minus sum over k. So wait, let me write this properly. Minus sum over k x ck del del yk, right? By linearity of the connection in the first argument, I can put these functions inside, right? This ybj I can put inside with the del del yj. So I get this sum over j ybj del del yj minus sum over k x ck del del yk, right? Yeah, so actually, yeah, right. So what is bj? Bj will be what I get when I so this is a vector, right? So I can apply dyj to this, right? So that will give me just bj. So bj is d yj of dfx, right? Yes.
Yes, sir.
And similarly, ck is dyk of dfy. Okay. So what is ybj? Ybj is y acting on this. Okay. This is a function. So yeah, so this is d of yj composed with f, right? Right, this acting on x. Yeah, so this is x of yj composed with f, right? Right.
Yes, sir. Right.
And similarly, this ck is y of yk composed with f, right?
Hmm.
So what is ybj? This will be yx of yj
Y
composed with f, and xck will be xy of yk composed with f, right?
Right.
And that's it. Yeah. So I make this a sum over this jk a dummy indices. So this becomes a sum over j ybj minus xck xcj, sorry, ybj minus xcj. Yeah, that's it. So del yj, right? This whole thing, nabla this acting on si, right? That's it. Yeah. So this ybj minus xcj will be what? This will be minus xcj. This will be yx minus xy acting on yj composed with f, right? So that is bracket xy acting on, or minus bracket xy acting on yj composed with f. So that's 0. Okay. Is this all right? Yeah. So this term here, this is 0. Is this clear?
Yes, sir.
Yes.
sir.
Okay. Yeah. Sorry for slightly messy calculation, but it works out. So finally, what do we get? This extra term vanishes. So all we have left is r of dfx, dfy acting on s. That's it. So we get the formula for the pullback connection. Thus, r bar of xy acting on s. This is r of, so r is the connection on E, okay? The curvature of E, sorry, r is the curvature of E. So that takes in tangent vectors in N, right? Which are dfx, dfy, and acts on the section. I mean, what this means is, let me write it properly. This means for all P in M and VW in TPM, R bar of VW acting on S, okay, at P this is equal to R of DFPV DFPW. So this R of DFPV DFPW, this is an endomorphism, right, of E at FP, right? Yes. Because R is the curvature of E, right? So this is R at FP. Is this clear? R at FP acts on tangent vectors at FP, right?
Yes, sir.
Tangent vectors at FP are DFPV, DFPW. So R at FP acts on these two tangent vectors at F of P to give you an endomorphism of TF of E at FP, right? And that acts on S at P. S at P is an element of the fiber of E at FP, right? Is this clear? Okay, so the whole thing gives you what? The whole thing gives you an element of E at FP. All right.
Yes, sir.
Yeah, E at FP is what? That is the fiber of F star E at P. Is this clear? Yeah. Okay. Yes.
Yes, sir.
Yeah.
This was okay. So this is the curvature of the pullback connection. All right. Okay, so now we can come to the Bochner-Weizenbach formula. Okay. So before doing this, so we have F from M to N. So I have the energy density of F is half norm dF squared. So this is half inner product dF. Okay. Remember, this inner product of AB is trace of B star A, right? Okay. That's the inner product on the bundle of linear maps, right? From Tn to F star Tn. And now to do the calculation, we fix a point P and M. Okay. And what you can do is you take an orthonormal basis of TPM and then you parallel transport along geodesics passing through P. Okay, so you take a ball, a geodesic ball around P, and then I'm taking all the geodesics passing through P. Right, what I do is I have my orthonormal basis here. Right, you parallel transport it along all these geodesics. Okay, so that will give you vector fields, n vector fields to get. So which will form a basis of the tangent space at each point. So this is called a local frame. And because these vector fields are orthogonal at P, and I'm using parallel transport, which acts by isometries, these vector fields will be orthonormal at every point in this neighborhood of P, right? To get n orthonormal vector fields E1 to En on a neighborhood of P, okay, such that so because at P, these are given by parallel transport along geodesics passing through P, that means the covariant derivative of any of these vector fields along a geodesic, along a curve passing a tangent vector at P will be 0, right? Because this covariant derivative, nabla V EI, this will be 0 for all vectors V at P, right? Because the EIs are given by parallel transport along geodesics passing through P, right? This is P. So if I take a vector, my say E1, right? E1 is given by parallel transport, right? Along this geodesic, say. So if this vector is say V, what will the covariant derivative of E1 in the direction of V be? It will be 0, right? Because it's given by parallel transport in this direction, right? Yes?
Yes, yes.
Yes, sir.
Yeah, so all the covariant derivatives of these vector fields at the point P will vanish, okay? At the point P, all these covariant derivatives will vanish, okay? So in particular, this means that nabla, say, EI, EJ, this vector field, this is 0 at P for all IJ, okay? All right. So this EI is called a local orthonormal frame. Okay. So these are very useful in our computations. We'll always be using these. And so we can always choose a local orthonormal frame so that the covariant derivatives vanish at a given point P. Okay. All right. So nabla, this EI is called a local orthonormal frame. Okay. Fine. So let EI star be the local dual basis. Okay. All right. So what is EI star? So if this is the dual basis coming from an orthonormal basis, then EI star acting on a vector V will be what? What will it be?
Inner product.
Inner product, right? It just be the inner product of V with EI, right? Okay. Right. The dual basis, if you take an orthonormal basis, then the dual basis is given by inner product, right? With the basis, with the orthonormal basis, right? Yes. Yes.
Yes, sir.
Okay, fine. Okay, so now recall for the, so this is EIs are sections of the tangent bundle EI stars are sections of the cotangent bundle. These are one forms. Okay. Now we already computed the curvature of the dual bundle. Okay, so that satisfies R of EJ EI acting on some EK. So let me take in EK star. Okay. So we proved, let me show you this formula. So yeah, so this okay, so let me do a general yeah, so okay, so we did prove this formula. So for the, okay, let me just give you the general formula. So instead of this particular case, which we'll need. So for UV in TPM and so UVW. So if I take 3 tangent vectors, and if I take an alpha, which is a cotangent vector, so I can look at the curvature of the cotangent bundle with respect to the connection on T star M induced from the Levi-Civita connection on TM. Okay. So I take the curvature of the cotangent bundle. I'm just going to use the same symbol R for all of the curvatures. So R of UV applied to alpha, this will be what? This will be an element of the cotangent space. Okay. So this will act on W. Right. Okay. And what we showed is this is curvature of the dual bundle of T star M. This is going to be minus alpha acting on R of UV acting on W. Okay. So be careful. This R here is the curvature of the cotangent bundle. This R here is the curvature of the tangent bundle. All right. These are two different curvatures of two different bundles. They're related by this formula. Okay. If you remember, we proved this formula. Do you remember, any of you? Yes.
A special case was done, right? Or was this one?
We proved this formula, yeah, for the curvature of the dual bundle, right?
Yeah, okay. Huh.
Right. We computed the curvature of the dual bundle, right? So then we proved this formula. Okay. All right. So using this, we can prove the following lemma. So let Rn be the curvatures of Tm and Tn for the Levi-Civita connection. Okay. All right. So then let me see here. Yeah, so, okay. If I look at R of EJ, EI, so I want this to act on DF, okay? And then this, I will act on EI, yeah. Sorry. Okay. So this will be able to write in terms of the curvatures of M and N. But first understand what this is, okay? This DF, this is a section of a tensor product bundle, right? T star M tensor F star Tn, right? Yes. So on that, we have an induced connection. This R, this is the curvature of the connection on, this is the curvature of T star M tensor F star Tn, okay? Is that clear? So this acts on this section of this T star M tensor F star Tn to give you another section of T star M tensor F star Tn, right? So that is a linear map from Tm to F star Tn, right? So that will act on this section of Tn, all right? Is the meaning of the symbols clear?
Yeah, it's clear.
Okay. So this curvature we'll be able to write in terms of the curvatures of M and N. Okay, so let's stop this session and start a new one. Okay. Okay. All right, so let's continue. So we'll work out a formula for this, right? So let me not write it first. Let me do the calculation. Yeah. So first of all, we have to write DF as a section of this tensor product bundle. So that we know DF is a linear map, right? So with respect to the basis EI, I can write this as a sum over I. Or maybe I should take us 1 second. A sum over K. Yeah, I should write it as. Yeah, so I'm fixing I and J. So let me write this as a sum over K. Of EK star tensor DF of EK, right? Yes?
Yeah.
Right? Okay. Now, so what is going to be R of EJ, EI acting on DF? So remember, the curvature of the tensor product bundle is the curvature of the first bundle tensor identity plus identity tensor curvature of the second bundle, right? Yes?
Yeah, yes.
So this is going to be sum over K R of EJ, EI, EK star. So this thing is this whole thing is a element of the cotangent bundle tensor DF EK. Sorry, what am I doing? Yeah, tensor DF EK plus sum over K EK star tensor R of EJ, EI applied to DF EK. Okay. Yes.
So that is now then the like Riemann curvature, right? I mean, just curvature on the tangent one.
Which
The
one?
R of EJ, EI, DF, EK. I mean,
No,
on
no,
the
no, no,
right.
no, 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 no. This is the curvature
Oh,
of
that's
the
F star
pullback.
TN. Sorry.
This is the
F
curvature
star
of the
TN, sorry.
pullback bundle. Yeah, this is
Yeah, F
curvature
star
of the
TN.
pullback
Sorry,
bundle.
sorry.
Yeah, right.
F star TN.
F star T. Yeah. So okay. So what will this be? So this will be. So if I apply this whole thing to EI now, what will I get? So R of EJ, EI, DF. The whole thing applied to EI will be what? So basically the dual elements are going to act on the EI, right? So in this sum over K, I'll get sum over K. What will I have? R of EJ, EI, EK star. This whole thing acting on EI, right? Okay. So this is a scalar, this into DF EK, right? Okay. Plus, I'll get sum over K, then EK star acting on EI, and then I'll get into this vector R of, so R of EJ, EI acting on DF EK. This is the curvature of the pullback bundle. This we know what it is, right? Okay, I'll write that in the next step. So, well, we can write it here. This is going to be R of DF EJ, DF EI. This is now the curvature of TN, okay, acting on DF EK. All right.
Yes. Yes.
Yeah, so that's what we proved about the curvature of the pullback bundle. Okay. So I should write here, this is curvature of F star Tn. And this thing here, this is curvature of Tn. Okay.
Sir.
Yes.
So this object REJ, EIDF acting on EI, this is an element of F star Tn, right?
Which one?
This
Yeah, this
the
the
first
first,
thing
this
that
one,
you-
this one. REJEI acting on DFEK.
only DF,
Oh, only
and
DF.
then that whole thing is acting on EI. That is an object of F star Tn.
Yes. Yeah, this thing you're asking about this.
Yes, right.
Yeah, this is a section of F star Tn.
Okay.
Because without the EI, it's a section of T star M tensor F star Tn.
Right.
And then the T star M component acts on the EI. So that becomes a scalar, then it becomes a section of F star Tn. Okay?
Okay.
Right? Okay. So now let's compute this. So this R of EJ, EI, EK star acting on EI, this first term we saw, this was minus EK star acting on R of EJ, EI acting on EI, right? Yes? Right. This is what we saw from the curvature of the dual bundle, right? Yes?
Yes.
Okay, so maybe I should write here. This thing is the curvature of T star M. Okay. Okay. So now this thing is the curvature of Tn. Okay. So I have this plus I have Now the sum over k, this ek star of ei, this is going to be 0 unless k is equal to I. Right, so here I'll just get one term. When k is equal to I, this becomes 1 into this. So I'll get just, this is now Rn of df ej df ei acting on df ei. Okay, so that's one term. And this other term here, this is sum over k. So I have minus the inner product of ek with r of ej ei ei, right? df ek plus this other one term, yeah, plus Rn of df ej df ei acting on df ei. Okay, so now I can use the fact that the curvature of the tangent bundle, because the parallel transport acts by isometries, which are orthogonal linear maps, the curvature acts by skew symmetric linear maps, right? So this R of ej ei, this is an endomorphism of the tangent bundle. This I can take to the other side as its adjoint, right? But the adjoint is minus the linear map, and there's another minus sign here. So those two minuses will cancel. That means that this R of ej ei will just come to this side, right? So this will become sum over k inner product R of ej ei ek ei into df ek, right?
So minus of R EJEI, the
Let me just write
adjoint
that.
of that is.
Let me just write this here. R of ej ei star is equal to minus of R of ej ei, right? The curvature tensor of Tm is an endomorphism valued 2 form, which takes values in skew symmetric endomorphisms, right? It takes values in skew symmetric endomorphisms. Therefore, we have this, right? Is this okay? The minus signs cancel. Yes?
Yeah, it's okay.
Okay. All right. Okay, so let me just check. This is what we have here in the notes. Yeah, that's exactly the formula that we have. So, okay. So this is a curvature of M. Okay, so we get this formula. So let me just write it here in the beginning. So this is equal to sum over K inner product Rm Ej Ei Ek Ei df Ek plus Rn df Ej df Ei df Ei. Okay, fine. So that's what we've proved. Okay. Okay, so now we can come to the Bochner-Weizenbach formula. Yeah. So let me state the formula at least. So it says the Laplacian of the energy density EF, this is equal to the norm of the second fundamental form squared what are the, I'm just checking the signs. So plus sign or minus, plus, yeah, okay, fine. Plus the inner product between nabla tau f and df, okay, plus the trace of df star df into Ricci curvature of M. So remember, this Ricci of M is an endomorphism. So this into df star df, that's also an endomorphism. The whole thing is an endomorphism, okay? And then minus, I have the sum over ij. I have some curvature terms, Rn df ei df ej acting on df ei, inner product df ej. That's it. Okay, this is the Bochner-Weizenbach formula. Okay. Is the statement clear?
Yes, sir.
Okay. So I have to tell you what this nabla df norm squared is. This will be the sum over ij, nabla df of ei ej norm squared. Yeah, that sum. Okay. So that's what this norm df squared is. Okay, so let's first compute the Hessian of the energy density. So if I take the Hessian of EF acting on EI comma EI, right? What will this be? So this by definition is the inner product nabla EI of the gradient of the energy density, inner product with EI. Okay. Now by the metric compatibility, this is EI of the inner product between nabla gradient of the energy density with EI, right? This minus nabla EF inner product with nabla EI EI, right? Yeah, this is just by the metric compatibility, right? Yes?
Yes. Yes.
Yes, sir.
Okay, but this nabla EI, this is 0. So this this is 0 at P, right? So I'm computing everything at P, okay? So at P, I can forget about this term. So I get just EI of this nabla EF EI. So what is the inner product of nabla EF with EI? By definition, that is EI acting on the energy density, right? Yes? Right. This is the derivative of the energy density acting on EI, right? So that is the same as the EI acting on the energy density, right? Okay. Yes? Okay.
Yes, sir.
And right. Now, what is the energy density? It's half inner product df df, right? Okay. So EI acting on this inner product df with itself by metric compatibility on the induced on the tensor product bundle will give you 2 times nabla EI df inner product df, right? So the 2 and the half will cancel. So you'll get nabla EI df inner product df. Okay. Yes. Now EI acting on this inner product will give you two terms, again by metric compatibility. So you'll get nabla EI df inner product with df plus nabla EI df inner product nabla EI df. So that will give you norm of nabla EI df squared. Okay. Yes. Okay.
Yes, yes.
Okay. So what is the Laplacian of the energy density? This is the sum over I. It's the trace of the Hessian. So sum over I, nabla squared EF acting on EI. Right. So there'll be two terms. One is this sum over I, norm of nabla EI df whole squared, plus then you'll get sum over I inner product of nabla EI df, right? Okay. Yes. So this first term is what I'm calling the norm of nabla df squared. Okay. All right.
Yes, yes.
So this is my definition of nabla df squared. It's just this sum. All right. What you can check is actually this is independent of the choice of orthonormal basis. So this is actually an intrinsic norm squared. Okay. All right. So I get the first term in the Bochner-Weizenbach formula. All I have to show is this sum is equal to the sum of the other three terms in the Bochner-Weizenbach formula, right? Yes.
Yes, yes.
Okay, so I'm just going to look at this term now. Okay, so I have this sum over I inner product nabla EI df. So now both of these are this is an inner product between two linear maps. So that is the same as the sum over J of these linear maps. Right, acting on EJ and inner product with DF EJ, right? Yes. All right, this is by definition of the inner product on the bundle of linear maps. Yes.
Yes, yes.
Okay, fine. So now what I want to do is write this term. Yeah. This I can write as nabla EI of nabla EI df acting on EJ. Okay. So the whole thing in brackets, right? Minus nabla EI df acting on nabla EI EJ, right? Yeah, by the Leibniz rule. Right, nabla EI acting on this section of a dual acting on this section will be this plus this, right? So if I subtract this, I'll get this term. Yes, okay.
Yes, yes.
Okay, and now this nabla ei ej, this is 0. So at P again. So I can forget about this. Right, this nabla ei ej is 0 at P. So this term goes away. So this I can write as sum over I of sum over j. I'll get inner product of nabla ei acting on nabla ei df acting on ej. Okay, fine. This whole thing inner product with df ej. Now this thing inside is what? This by definition, this is the second fundamental form, nabla df acting on ei ej, right? But this is symmetric, so this is the second fundamental form acting on ej ei, right? So I can interchange ei and ej here. And so this will be a sum over I, sum over j. And then I'll get inner product, nabla ei acting on nabla ej df acting on ei, right? Df ej. Yeah, by symmetry of the second fundamental form. Okay. And now this thing again by the Leibniz rule, this is going to be nabla ei nabla ej df acting on ei. Okay. All right. Yes, because there'll be another term nabla ei, which is 0, right? So that's because nabla ei is 0 at P. All right. Is that clear?
Yes, sir.
Just like we did here, right? So we're doing the same thing down here. Okay. Okay. So now I'm going to use the curvature of this tensor product connection. So this nabla ei nabla ej acting on df, right? So what do I have? I have that nabla ei nabla ej df minus nabla ej nabla ei df. This is equal to r of ej ei df. Notice that yeah, the bracket of ei and ej is 0. Okay, so note that's by symmetry, because the bracket of ei and ej, right? This is nabla by symmetry. This is nabla ei ej minus nabla ej ei. This is 0 at P, right? So this is true at P, right? Yes. Okay.
Yes, yes.
So I can interchange these two and I'll pick up a curvature term, right? So let me do that. So then I'll get sum over I, sum over j, and then this nabla ei nabla ej I can interchange. I'll get nabla EJ, nabla EI, DF. Okay. This
So this is a third derivative, right? That's why you are
correct,
getting
correct,
cut
correct.
aside.
Exactly, exactly. This is a third derivative. See, in DF, you have a first derivative, and then I'm taking two more derivatives, right? So this is actually a third derivative. So here you will get a curvature term, okay? When you interchange derivatives here, you will get a curvature term. Exactly, that's right. This is what I was saying earlier, right? The third derivative is not symmetric, okay? So that's where the curvature terms in the Bochner-Weizenbach come from. Okay, so I'll get this inner product DF EJ plus I'll get the curvature terms, right? Sum over I, sum over J. Inner product of R of EJ EI. So this is why I did that lemma. This is exactly the term which comes up, right, in that lemma. R of EJ EI DF acting on EI. The whole thing in a product DF EJ, right? Okay. Yes.
Yes, yes.
And now in this first term, I again, I can put this, I can put this in brackets. Basically, I can write this as nabla EI, sorry, EJ acting on nabla EI DF of EI. Right, I can do this because, again, this is because nabla EJ of EI is 0, right? There's another term I would have got, but that vanishes at P. Okay, so I can put this in brackets here like this, right? And then I get the sum of these curvature terms. All right.
Yes, yes.
And this is what? This is the second fundamental form acting on EI, EI. Now, if I sum over I inside, I can take the sum over I inside, right? So this will be a sum over J of inner product of nabla EJ of sum over I nabla EI DF EI, right? This thing inside, this is just the tension field, right? This is tau F, right? Is it clear? Yes, just by definition of the tension field, right?
Yes,
Yes, sir, it is
yes,
clear.
sir.
Okay, so this is what? This is nabla EJ of the tension field. And then I'm taking inner product with DF EJ, and then I'm summing over J. So this gives me exactly the first term. This is the inner product of nabla tau F with DF, right? Is that clear? Yes?
Yes, yes.
Okay, and then I have what here? I have a sum over IJ. This curvature term, there were two terms, right? One was a sum over K. So I'll have a sum over K. So I've forgotten the formula. Let me just check. So you had Rm of EJEI, right? I've forgotten the formula now. Acting on EK, I think, right? No, what was it? Let me just check. Sorry, I've forgotten the formula. The lemma that we did, yeah. So R EJ EI DF acting on EI, yeah. So this is the sum over K, right? RM of EJ EI EK EI DF EK, right? So that was the first term, and then there's this curvature term. Okay, fine. So EK EI and then DF EK, right? Okay, so let me go back down. It's quite a long computation. EJ, EI, EK, and then EI. And then I had this into DF, EK, and then I have inner product DF, EJ. So this will be inner product DF, EK, DF, EJ, right? Okay. So that's one term. And then I have the sum over IJ. Inner product Rn DF EJ DF EI acting on DF EI, the whole thing, the inner product DF EJ, right? Okay. So that's it. That more or less does it. Okay. All you have to notice is that here we want to get a Ricci curvature. So what we do is I take the sum over K outside, right? So if I take the sum over K outside, the sum over JK outside, right? I take the sum over JK outside. And then inside, if I sum over I, what do I get? This will just be, if I sum over I, this stays fixed, right? So when I sum over I here, this inner product RM, EJ, EI, EK, EI, right? This sum over I, this is exactly the Ricci curvature of EJ, EK, right? This is reach M of EJ inner product EK, right? By definition of the Ricci curvature into inner product, this I write as DF star DF of EJ EK. Okay, so this is the jkth matrix coefficient of Ricci curvature. This is the jkth matrix coefficient of DF star DF. So this whole sum becomes the trace of DF star DF into Ricci curvature of M. Okay. And then finally, this last term becomes, I just interchange the EJ and EI here and I get what I want. I get a minus sign, sum over IJ, inner product, Rn, DF EI, DF EJ, into DF EI, inner product, DF EJ. Okay, that does it. Is that clear? Yeah?
Yes, sir.
Yes, sir.
That finishes the proof. That finishes the proof. Okay. So next time we will see applications of this Bochner-Weizenberg formula. All right. Okay, so I'll see you next Tuesday then. Okay. Yeah. Okay. So see you then.